Hey everyone, welcome back to Cells to Cell. My name is Heem, this is Nick, and this week we're actually going to be talking about CAR T cells. So CAR T stands for Chimeric Antigen Receptor. T stands for the T cells, so CAR T stands for CAR T cells.
Yeah, we just wanted to. Oh,
yeah.
my bad. Yeah, we just wanted to make this. This will be kind of like a quicker episode, but we've had a lot of guests on lately. We've done a lot. We've kind of gone outside the box a little bit with some of our Trivia Tuesdays just to switch it up a little bit. But this week we wanted to break up the interviews and just come back and do like a quick 10-15 minute episode just talking about a little bit more of regenerative medicine and some different cell therapies. So I believe on the show we've mentioned CAR T cells before, but we've never actually like gotten into, what they are, how they work. And honestly, the concept is great and the concept is really simple. So first, I think today we're going to just go over where do CAR T cells come from, how do you make them, and then how do you give them back to a patient, and how does that affect their body, and and what are they used for? So we're just going to gloss over just a quick summary of all that kind of stuff, and then talk about some FDA approved drugs and therapies, and just kind of how this is one of the coolest things in science right now, in my opinion. I think that the concept of, this combination of using, it's almost like combining immunotherapy and cell therapy. And immunotherapy is basically changing your immune system to fight off a disease or to fight off, cancer in this case. And that's what a lot of CAR T is targeted towards, is cancer. And, it's taking the immune system and ramping it up more than what it would have already done. And one thing that's really interesting that I've learned up here is that cancer is very evasive, and it makes sense because once you have cancer, it's really hard to get away, and the immune system is made to find cancer, but the cancer cells are really good at getting away, and that's why you're able to have these giant tumors, all around your body, and they can metastasize and go throughout the body and reside in other places. So why don't you go ahead and just talk about kind of the first step of CAR T cell therapy and kind of what the process is before we get into the nitty gritty, talking about FDA and everything.
For sure. So Nick did a pretty good job introducing everything. Something he mentioned that I think is super important when you talk about CAR Ts is that CAR Ts are under this category of immunotherapy. So immunotherapy basically means using your own immune system to fight your own diseases. So in your immune system, you have your white blood cells, you have your NK cells, you have your T cells. Now, these are responsible for communicating with your body, your cells, and if your cells see that there's this disease, there's this infection, there's this bacteria, they will release these little molecules that are sensed by your immune system, and then your immune system will create new T cells and will create B cells to remember what the disease looks like. But basically, these T cells, when they get activated, your body communicates with it and says, hey, this is what the disease looks like, go get them. Mm-hmm. So then these T cells will be engineered by your own body naturally to go fight a disease. So that's what happens naturally, So scientists were like, okay, if this is what's happening naturally, if this is how your body naturally talks to your immune system to kill bacteria or something, can we use the same mechanism to fight other things in your body? So what researchers did was that they created this entire process, but I'm just going to go over the simple version of it. You take out T cells from somebody, you engineer them so it looks for this specific cancer, and then you put them back in that person. So for multiple myeloma, a type of cancer, a scientist will take out your T cells, so your already existing immune cells, engineer them so they target this multiple myeloma cell in your body. So this T cell will have a receptor on the outside which targets only multiple myeloma, and then these T cells will be put back in you, and because they're your own cells, it does fine, and because it's an immune cell, and it does well with killing stuff and finding things in your body to defeat, it goes around, and since you engineered it for multiple myeloma, it'll go in multiple myeloma and target that.
Yeah, on paper, it sounds like the perfect therapy. It sounds, like something that's going to be effective because we know that our T cells in our immune system are very effective when fighting off foreign invaders or even our own cells that are sick or dying. And, it sounds effective because if you're only targeting that single cell, then what else could go wrong? And while CAR T cell seems like the perfect therapy, it definitely has its issues, and researchers are still working very, very hard to figure it out. But as they've had issues, they also continue to push forward because these CAR T cell therapies are really only used for myelomas and lymphomas, right?
Yeah.
So these are more, let's call them liquid cancers. They're cancers of the blood, right? We still cannot use these for, say, breast cancer or any solid tumors found throughout the body.
That's true.
Because it's very hard. We've spoken about the microenvironment of cells on this podcast. Just the environment that occurs around a cell and how it pushes things outside and how it reacts to other things from outside. Because our cells are not in a vacuum. They all live together in a 3D environment and they all communicate, which I think is one of the coolest things ever. But understanding that the tumor microenvironment is very, very immunosuppressive, meaning that it pushes away the immune system from attacking it. The immune system understands that this cancer is bad and that it's hurting, the body, but it literally cannot get into it. And these CAR T cells, through what's called transfection. So transfection creates what are viral vectors, and that's how we get these new antibodies or these new receptors on the outside of the cells, as he was saying, that can target the bad cells, the cancer cells. And using either a lentiviral vector or a retroviral vector are the two different vectors that you can use to infect your T cells and put them back into your body to search for this cancer. They're getting a lot better at how can we break through the microenvironment and get into, the tumor microenvironment of a solid tumor. And that's kind of, I feel like there's two branches right now in CAR T cell therapy research. It's figuring out the issues and how we can fix them, and then also pushing forward and how can we get more specific and get into solid tumors.
I think something important Nick mentioned again is the microenvironment. So there are some cancers that can just literally circulate throughout your bloodstream, okay? We call those liquid cancers. They're not part of a solid tumor. They're not solid tissue like your heart, like your breast. It's not like your bone. It's not like your eyes. It's not like your skin. These liquid cancers just keep circulating. And your immune system has these T cells also circulating. So imagine they're just circulating, and then when your T cells run into them, they'll kill them. So it works out that way. But if you have a cancer on your liver, for example, okay, then your T cells can go there, but they don't do as well because in this microenvironment of the liver, your cancer cells over there are in control of that entire microenvironment. So they'll see the T cells coming, and then they'll block them off, evade them, get rid of them so they don't die. And the cancer keeps growing and surviving, right? Mm-hmm. Whereas if it's a liquid cancer, they don't really have a microenvironment. They just keep circulating. They don't have really an opportunity to evade the cancer like a solid tumor does.
Mm-hmm. I think... Have we said what you said what the CAR stands for, right? Chimeric Antigen Receptor. So what that means is there was at first the first CAR was just like it was called like the first generation. And it's the protein on the outside, the receptor, and on the inside there was a mechanism that occurred when it attached. And now we're all the way up to generation 3 where there are 3 pieces it's 2 pieces on the inside. Or maybe is it 3? Is it 3 pieces on the inside? Or is it the top? I believe either there are 3 different protein complexes on the inside that would either count, or the outside protein counts as 1, and then there are 2 on the inside. But what those do is it causes these T cells to change, and it actually, I believe it causes their affinity to become even more, to bind to those cancer cells more, to be even more effective and more potent.
It is true.
So,
because, for example... Let's say some cancers, we've talked on this channel before about cell surface markers. So let's say cells in this entire arm here, let's say they express CD135, CD45, and CD23, okay? Now, 2 out of 3 of them are expressed in cancers, and 1 out of 3 of them are expressed in normal cells. and three out of them are expressed in super highly aggressive cancers. Okay? Now, if we want our T cells to only target one of them, we need to have a very, very, very specialized T cell. So what Nick was mentioning with this cascade, these T cells, these third generation T cells, the inside cascade now is kind of like a selection process. If a cell is CD this, and CD this, then you can kill them. So now this next generation of T cells is evolving, so it's not like you get highly, highly, highly specified cells because selection, because if you have millions of T cells going around you and you have a cancer in your arm here and CD23 is on all of them, you need something that's more specific to the cancer so you don't kill everything. So CD23 plus CD45 plus that 145, and that will highlight your cancer cells and kill them.
And that's important because specificity and having a specific target rather than just monitoring the entire body and attaching to whatever might match kind of close is really important, because the biggest problem with CAR T cells is a lot of times when you inject it into somebody, so you've taken them out, you've separated the T cells from their red blood cells, you've infected them with the whatever gene you want, and you've tested to make sure that they're safe. Even after the safety testing, you can still put them back in, and there can be so many adverse effects or side effects from these CAR T cells that can lead to a very, very quick death, which is really sad.
Yeah.
Talking about like these intense cytokine storms where just like your immune system just starts attacking everything.
Yeah.
That is not what we want. We only want to attack those bad cancer cells. We cannot be attacking healthy cells that are doing good throughout the body, because why would we want to attack something that's helping us, right? We want to attack the cancer. So go ahead, Heem, and pull up so CAR T cells, while they're still very new, as of the last couple of years, there are, 6 or 8?
There are almost getting to double digits, but higher up in the single digits, around 6 to 8.
So it's like 6 to 8. There are 6 to 8 CAR T cell therapies that are actually FDA approved, that you can actually receive in the clinic. Now, we've talked about pricing in FDA before. I don't know how much they cost, but he can just throw out a couple names and maybe what they do.
So this is a pretty recent technology. It's been developing, but having success with it is huge. But in 2017, Chimera was a breakthrough CAR T therapy that FDA approved for B-cell lymphoma. And then later in the same year, so in 2017 again, Yescarta is another CAR T therapy that got approved for another B-cell lymphoma. So the first two ever approved in the United States were for B-cell lymphomas. 2020, T-Cardis was approved for non-Hodgkin lymphoma, so once again another lymphoma. 2021, Breyanzi received FDA approval for large B-cell lymphoma again. And in 2021, Abecma got treatment approved for multiple myeloma. So 4 out of 5 of them for B-cell lymphomas, acute and non-Hodgkin's and all kinds. And the other one was
multiple myeloma. Right?
Multiple myeloma.
Yeah, so we're starting to see that the first ones were very specific.
Yeah.
Very specific to B-cell lymphomas. But in the last couple of years, we started we're still in liquid cancers. We're still in, the lomas, you could say, the lomas. But as we continue to move through the liquid cancers, we will then start seeing applications for, small solid tumor cancers, and eventually move up to bigger ones. And, everybody's looking for the cure to, breast cancer or brain cancer or prostate cancer, something like that. And this is one of those therapies that really shows a lot of promise.
Definitely. And as you can see, like the FDA in the past few years has slowly been ramping up things to be more competitive in the world for cell and gene therapy products. As you can see, even though they're T cells, even though they're immune cells, they're still considered cells. So this is a cell therapy. Even though it's immunotherapy, the FDA is going to categorize this as a cell therapy. So the same thing as stem cells. A stem cell will be a cell therapy. a T cell therapy is also a cell therapy.
Yeah.
And it's not like you're taking Tylenol. Tylenol is like a little chemical.
Yeah.
That's not a cell. So you don't need FDA approval for it. You do, but when it comes to like cell therapies, it's a whole new ballgame.
It is. It is a whole new ballgame. And I think in our earlier episodes, we really hit home on the FDA and how they treat cell therapies versus, what I like to call, small molecule drugs or even big molecule drugs. But really, it's just looking at single molecule. How does it affect animals, then humans, and then you go through dosing phases, safety phases, that kind of stuff. But I think that this is very promising, not only for CAR T cell therapy, but for all kinds of cell therapies, including stem cell therapies, that in the last 5-6 years, we've actually been seeing some progress with this, where in 2010, this probably would have never happened.
Never.
So, no, I think that CAR T cells, like I said, very, very promising. If researchers can really get the safety right, I think that they've hit a home run.
It's the beginning of autologous therapies.
Yeah,
dude.
it really is.
It's the beginning of you donating to yourself. You don't need another donor.
Mm-hmm.
You just donate to yourself.
So, all right. Well, I think that does it, Heem. I think that was a good episode. I hope this was, informative to you guys. Again, we try not to go too far in depth. If you have any questions, go ahead and comment down below. But we really appreciate you guys watching. So, Heem, do you have anything else for this episode?
That's all.
Awesome. Well, this has been another episode of Cells to Cell. So I'm Nick. That's Heem. Thanks, guys.
See you guys.